Hello everyone, I'm Yu Wei, an application engineer from NOVOSENSE. What I will share today is how high-precision voltage references from NOVOSENSE can help customers. There are three parts of my presentation. In the first part, I will present the factors influencing the selection of a voltage reference. The second part is about voltage references from NOVOSENSE, including NSREF 30 series and NSREF 31 series product families. In the third part, I will use NSREF 3130 as an example to explain how voltage reference errors affect the ADC acquisition system. When choosing a voltage reference chip as reference voltage, you need to consider the following elements of the system architecture: supply voltage, power budgets, load capacity, temperature range, package size, and price. When the basic requirements of the system are met, it's necessary to consider whether the parameters of the voltage reference meet the requirements. High precision and low noise are the basic performance requirements for a voltage reference. A voltage reference must be stable under changes of different external environment factors, such as temperature, environmental stress, and time. All these external environment factors can affect the performance of a voltage reference. There are different parameters used to measure the performance of a voltage reference, such as initial accuracy, temperature drift, noise, thermal hysteresis, long-term drift, voltage regulation, load regulation, and drop-out voltage. NSREF 30 series and NSREF 31 series from NOVOSENSE are two voltage reference product families. Each product family has 6 output voltage options and do not require a load capacitor to be stable. In terms of temperature drift, NSREF 30 series provides a maximum value of 35 ppm per degree centigrade, while NSREF 31 series has a better performance, with a maximum value of 15 ppm per degree centigrade. With regard to other parameters, the two voltage reference product families have same performance. For example, the maximum initial accuracy is ±0.2% for 2.5V output voltage. The typical value of 1F noise is 22 UV peak-to-peak value. The typical value of drift in the first 1000 hours is 100 ppm, and they provide sink current and source current capacity with typical value of ±10 mA. Temperature drift is caused by defects and non-linearity of the circuit, so it tends to be non-linear. For the measurement of temperature drift, NOVOSENSE voltage reference adopt the box method. The calculation of temperature drift is only based on the maximum and minimum values of measured voltage at a finite number of temperature measuring points and does not consider the temperature point at which these extreme values occur. Therefore, for a device having non-linear temperature drift, its temperature drift parameter cannot be used to show that in a narrow temperature range, the device's temperature drift performance will be better than the specified value. The output voltage noise of a voltage reference is generally reflected by low-frequency 1F noise and broadband white noise. In actual applications, broadband noise can be suppressed by compressing bandwidth, while 1F noise is difficult to suppress, which is one of the main sources of error in high-precision measurements. It can be seen from the table that under similar static power consumption and temperature drift performance, the output voltage noise of NSREF 30 series and NSREF 31 series products is far lower than mainstream products on the market. In actual applications, to reduce the effects of long-term drift of voltage reference on the system accuracy, a typically feasible method is to carry out regular calibrations. However, regular calibrations can lead to problems like reduced productivity. Therefore, the inclusion of long-term drift parameter is particularly important for the design of precision systems. Long-term drift refers to the drift of the output voltage over time. The long-term drift specified in the product manual refers to a drift of 100 ppm of the reference's output voltage in the first 1000 hours, rather than a drift of 100 ppm every 1000 hours. Long-term drift is mainly caused by mechanical stress and aging. The early drift of voltage reference is mainly introduced by mechanical stress, which usually causes a big drift of its voltage. Over time, package, welds, and chip materials become increasingly stable and the drift gets increasingly less. To estimate the drift over a longer time, the square root formula normalized to the drift over 1000 hours can be used. Thermal hysteresis is caused by changes in the mechanical stress on the chip, caused by thermal cycle. At a given temperature, after a relatively large temperature cycle, the thermal hysteresis can be observed, which is mainly reflected by changes of the output voltage. Thermal hysteresis is often overlooked. In a calibrated systems, thermal hysteresis can reduce the effectiveness of initial accuracy calibration, becoming a possible main source of error. In this part, I will use NSREF 3130 as an example to analyze how the performance of a voltage reference can influence the ADC system. The root sum square RSS method, based on statistical tolerance analysis, is typically used to calculate the system error. This table shows the items and value of error of NSREF 3130. In this example, errors in such parameters as line regulation and load regulation are omitted. The equation shows that the RSS method is used to calculate the overall error, and that the overall error of the voltage reference is converted to LSB of ADC. It can be seen that the error caused by NSREF 3130 to a 12-bit ADC is 13 LSB. After system calibration, errors caused by initial accuracy can be eliminated, and the temperature drift and long-term drift can be improved by 80%. According to the calculations, the overall error caused by NSREF 3130 to the system after calibration is 2 LSB. That's it for my presentation on how high-precision voltage references from NOVOSENSE can help customers. Thank you.